We began the Chapter 18, which is what I would identify as a third big picture topic in the study of chemical reactions. So in Chem 2, if you recall back when we first started this, I identified this course, or the first half of the course, or 90% of it, as the methods for studying chemical reactions. Now, in the study of chemical reactions, three big picture topics, two of which we've covered reasonable detail. Chemical kinetics, chemical equilibrium, and now chemical thermodynamics. Chemical kinetics, as you recall, focused on rates of reaction in terms of rate laws. And we looked at the rate laws as evolving from rate factors, the can't-see issue. I know you recall that as much as I talked about it. Concentration, area, surface area, nature, temperature, energy effects, and catalyst. So when we talk about kinetics, we approach the study of chemical reactions based upon those rate factors, and we construct mathematical rate laws. We then bridge into chemical equilibrium, and we look at the mathematics or analysis of that in terms of extent of reactions. And this was expressed in terms of equilibrium constants that we defined as K. And the larger the K, the greater the extent of reaction, or the more products. And the smaller the K, the fewer products are generated. Thermodynamics has twofold, this is a double-edged sword in this one. The definition of this, of course, is the study of chemical energy, changes in energy in chemical and physical process. So that's by definition. Now, I'm not minimizing this because this would be the focal point, certainly. But to me, the most important objective is to you to understand how thermodynamics is used to define the feasibility of a process. So the purpose of thermodynamics is to define feasibility of chemical or physical processes. And it boils down to, will it work or will it not work? Now, to give you an analogy of the idea of feasibility, I give one that everybody can easily relate to, and what that refers to is an incline, a flat, level surface, and I'm going to put a backwards incline for specific reasons. like this. The incline, what we do is we place a sphere, a ball, on number 1, case 1 at the bottom. Case 2, we place it right in the middle of the diagram. And case 3, we place it on the edge, not on the flat part back, but right up here on the top end. Without any outside help, what's the chance of case 1 ball rolling uphill without any help?
Yeah.
I mean, use your, just realistic idea. There's no chance on planet Earth right now. Now, we're not in outer space, we're on the surface of the Earth. So the thing would just lay there, wouldn't move. This is referred to as non-spontaneous. The second case right here, what's the probability of it moving? It has no tendency to go up or stay down in terms of moving from its zero position right here. So we say that that is at equilibrium. Now this proposes a static equilibrium, static physical equilibrium, but the chemistry will be dealing with dynamic equilibriums and relating that to thermodynamics. We'll get to it in due time. Now on this case 3, we've got the ball sitting there and maybe your finger is holding it. Then you remove your finger. Will the ball roll downhill in the reference frame we're in? All those in favor of it rolling downhill on its own, raise your hand. Okay, thank you. I'll make sure you're listening. So we call that spontaneous. So our objective here in thermodynamics is to develop chemical analyses that will lead us to whether or not a reaction is spontaneous at equilibrium or non-spontaneous. Okay? Now, for any chemical process going from reactants to products, you can expect an energy change. That's long and the short of it. Energy change. There may be 3 kinds of energy changes, and 2 you are very familiar with. This energy changes can be exothermic, isothermic, or exothermic. That's the endo. And we have briefly talked about this in terms of system and surroundings. When we describe energy change in a chemical and physical process, we're describing it relative to the system or the chemical reaction we're studying. But we measure all our observations in the surroundings. We don't measure anything in the system in itself. We measure the signals that come from the system. And in this case, heat flow, thermometers, thermocouples, and those devices. So an energy change, as we recall, is the gain of energy by the system. I'll write the last one. Or loss of energy by the system. System's getting colder. Or gain of energy, system's getting warmer. Isothermic means the net change in energy is zero. Change in energy equals zero. It's an isothermic change. To understand how this fits into the concept of thermodynamics, we need to review the heat flow, a T-table. And on the left, we'll put the system. On the right, surroundings. The system is the object of interest. Or in chemistry class, the chemical reaction. The surroundings is simply everything else. So when we measure a change in energy, we're measuring heat flow. So when we talk about these changes, is heat flow. Now, it's represented symbolically by several symbols. Delta H, you'll see a delta E, you'll see a lowercase q, you'll see a capital Q, and there may be some others. But those are the ones that are used most frequently in talking about energy changes. If we are observing a chemical reaction, that reaction is a system within itself, including the reactant side and the product side. Not just the reactants, not just the products, but the whole thing is the idea. Now, this can do one of two things. It can give off energy, and if it loses energy, we refer to that as an exothermic process. Or if it gains energy, it is defined as, of course, the endothermic. Now, what you need to focus on here is where are you making your measurements? Your measurements are made over here. And they are detectors of signals sent by the system. So you are essentially an observer, part of the surroundings, and you are detecting signals, language, sent by the system. This language is the language of the universe. Einstein made the comment that in order to understand the secrets of the universe, you must first learn its language. And that comes in various physical or chemical observable issues, things that you as an observer can detect. Some things you will have to have an instrument to detect it. Some things you do not. You as an observer have 5 senses that are antennae, and those 5 senses detect heat, light, electricity, cold, hot, and on and on and on. And it's just not a so what. You respond to that. Okay? Your response to whatever you're observing or the language that you're receiving is always interpreted in terms of what the system is doing. So as an observer, you're detecting signals sent by the system. But the observer interprets signals in terms of the system. Example is, take the reaction that I've diagrammed here, losing energy, the exothermic idea, and you take a thermometer and you put it in a liquid that's holding the reaction, the liquid would get warmer. You're detecting what the system does to the liquid. The liquid increases. But keep in mind, the reaction is getting colder. It's losing energy. And vice versa if we use the sample. Now, you can put your finger in there, and some of them are intense enough that you can feel it getting warm. And some of them are intense enough that you put your finger in the solution, and you'll get cold. Ammonium bromide dissolves, it'll get cold. The solution will drop in temperature. So the first thing you have to do in thermodynamics is identify the difference between the system and the surroundings, because the data interpretation sometimes is opposite what the system is doing, implies something opposite. I have an experiment set up, burner system, that's what I like to use, and we're going to look at the reaction magnesium and hydrochloric acid in aqueous solution. Now on paper we can draw the products of this in the following format, like that. Now essentially here is a reaction container, and we have an HCl solution, and you as a researcher add powder form magnesium solid into that. Now you would have a detector, maybe a thermocouple to a computer, or thermometer. And when you added that magnesium to the HCl solution and turn the data recording on, what you would observe is short piece of graph there, and then it would go up very rapidly based on the amount you put in, and then it would start leveling off and taper off and show you that graph. This was the T sub O, and the max temperature on this, I have to look at my wooden one. It's right here in front of me because I had it. So on completion of the reaction, when it reaches thermal equilibrium or reaches its maximum thermal point up here, that would be your T final. And fundamentally, as you look at this, so in our experiment, we observed the temperature to increase. Now, what's increasing in our observations here? Surroundings or the system? Anybody?
The system.
The system.
The system or the surroundings?
System.
No, it's the surroundings. Remember what we're doing. We're making a measurement, okay? And you never, ever, in any circumstances, measure the system. So the system is not going up in temperature. It's the surroundings that you're measuring, and it's going up in temperature. So our reaction, which is the black dot down here, is sending energy into the surrounding water, the solvent down here. And you are measuring the solvent. Well, if it's coming from the reaction, that means the reaction is getting colder or hotter? Anybody?
Colder.
Colder. Thank you. So you have observed a change and then interpret it in terms of, well, what's the system doing? It's losing energy. So the conclusion is the reaction is exothermic. And it's critically important that you understand this fundamental idea of scientific observation so that when you make your interpretation, it is relatively correct. You're making your terms relative to this reaction that's going on, not relative to the surroundings. You're measuring the surroundings, but interpreting your observation in terms of the system. The system is exothermic, but the surroundings are endothermic because they're gaining energy. But in classical interpretations, the words endo and exothermic refer to what's going on at the system level. So it's very important that I make an issue out of this now as we go through all of these concepts in thermodynamics, that you realize that what we're studying is methods of examining the reaction, the system, but also at the same time using devices to measure what the system is doing. And all the problems that you work, all the considerations, discussions, everything is revolving around, well, what is the reaction or system doing? Oh, I saw the temperature go up. Oh, everybody knows that's exothermic because we interpret it in terms of the system. We begin with the definition of energy. What is it? I usually ask the question, what color is energy? What does it taste like? Does energy exist? Yeah, we collectively agreed on this is energy. What was it? I'm not going to put this in here. The capacity to do work. That's what your physics book will tell you. The capacity to do work. Now work, says the physicist, is a force acting over a distance. And mathematically, that would be force times distance. From Newton's second law, we find that force is mass times acceleration. And then we include the distance. So, in terms of expansion of the concept of force, we get it into this expression. The units associated with mass in the SI, Standard International, is standard kilogram. The SI units for acceleration refers to meters per second squared. Go with it. And distance is SI units meters. When we combine this, we get a complex unit called kilogram meter squared over second squared. So those are the complex units of energy that has evolved from the definition of energy and work. Well, as a complex unit in the early days of thermodynamics, this was redefined as the joule. A joule is 1 kilogram meter squared per second squared. So as we get deeper into this, we will be using exclusively joules and calories, and rarely kilogram meter squared per second squared. Now, this is one of the two primary energy terms, units, that are used commonly. The other one, of course, is the calorie, the scientific calorie. And has a designation lowercase c. By definition, a calorie, 1 calorie, is the amount of heat needed to raise the temperature of 1.000 gram of pure water by 1 degree Celsius. We will run into another term in energy change called the heat capacity. That is used, but it's a throw off of these two. Is the amount of energy, heat energy, needed to raise a specified mass of substance by a specified temperature change. This is ambiguous for a reason, because you have the flexibility of choosing, as a researcher, choosing the size of the substance you want to use as your standard. Typically in chemistry, It's molar heat capacity. Which is simply defined in the context of what we've just said, the amount of heat necessary to raise 1 mole of substance by a specified temperature. That's called molar heat capacity. Molar heat capacity, capital C sub M. So there are 3 terms, including the joule up here, that are going to be used extensively. 4 terms, I'm sorry. Heat capacity, calorie, molar heat. Oh, there is one more. I forgot before I go into all of this. Specific heat. It's the amount of energy needed to raise the temperature of 1 gram of substance 1 degree Celsius. Now we talk about water. Its specific heat's 1 calorie. That means it takes 1 calorie, whatever the heck that is, 1 calorie to raise the temperature of water 1 degree Celsius. Now metals, they have lower specific heat. Some organics, they have higher specific heat. It takes more energy to raise a temperature. For metals, it takes less energy to raise, so there are fractions and things. We'll get to it. Now, one more. Phase transition. The amount of heat needed to raise a specified mass, correction, needed to evaporate, condense, freeze, or melt a specified weight / mass, usually 1 gram of substance. Example would be the delta H of fusion, freezing or melting of water, is equal to 80 calories per gram mass of water. So if I had 10 grams of water, I'd have to expend 800 calories to melt it, all 10 grams. So these are some definitions that we will be covering as we go through thermodynamics. And this is our language right now as we delve into this concept. There are 4 laws of thermodynamics, and we're going to approach 2 of them. And 2 of them we don't have time to go into, but I'm giving you what I consider as the most important aspects of this. 3rd law and 4th law, you can read up on those later. Now, where do the laws of thermodynamics come from? Chemical reactions, because thermodynamics is a method of studying chemical reactions. So we take a chemical reaction, it's going to give us an energy change. I think everybody's comfortable with that idea. But it also, are you listening to me? Energy change, oh yeah, we need that. But also, a chemical reaction will give us a change in the state of order of the products generated, and a change in state of order of products relative to reactants. So 2 issues are taking place. The energy change concept is the first law of thermodynamics. And is the study of energy changes in chemical and physical process. The second law of thermodynamics all systems tend toward a maximum state of disorder. By natural process, the ball is going to roll downhill. In other words, we're going to wear out and eventually move on to the fifth dimension, wherever that is, whatever it is. But there are analytical methods for treating reactions processes like this. It takes both of these together to define whether or not a reaction will work or will it not work. And we again refer to that, is a reaction spontaneous? Will the ball roll down on its own? Or do I have to put something into it that puts the ball uphill? That's a non-spontaneous chemical reaction. But we can drive a non-spontaneous chemical reaction. So example would be an electrolytic cell. You hook up batteries to it and you can conduct a current. But it will not proceed unless you put an energy into it. It's like rolling the ball uphill. We'll see how that works in due time. Classification of energy is broken down into a practical application or a physical or chemical application. The concepts that are applied, electrical, mechanical, nuclear, all use the chemical physical issues that we're about to talk about when we talk about energy, types of energy, and so forth. But you become an engineer, mechanical engineer, you'll be talking about mechanical energy. Well, it's still using these terms in the scientific classification, but you kind of think in terms of a mechanical issue. Or if you're a nuclear engineer on a submarine, and you'll think in terms of, well, the nuclear energy is this, that, and other, but it'll still evolve from the scientific concept of energy shown here. And we will focus from, I give this as a comparison, but we will focus our attention on these issues down here as we apply them. Now, there are three forms of scientific energy. The kinetic energy is energy of motion. Potential energy is stored energy or positional energy. You'll hear me use that terminology, positional energy. It's like putting something on a shelf. And we'll have positional energy in the concept of internal energy. And the difference is when we talk about positional energy in the physics world, we're talking about what is known as Newtonian potential energy. Placing an object on a desk relative to the floor, you can calculate some potential energy. Potential energy in the concept of internal energy refers to the changing of its structure and its state of existence. So internal energy is the one we will develop the first law around. Internal energy is energy of substance due to its structure and state of existence. State of existence, i.e., solid, liquid, or gas state. In that context, as we go through talking about these. Now, more on internal energy. through this, I'm going to use internal energy in two contexts. Positional internal energy and change in internal energy. Both of them, this one is a specified content energy as it sits on a relative scale. I'll show you that in a second. And a change in internal energy is simply the energy final minus energy initial. I'm putting in separated from internal. Initial. So if you have the final energy number and the initial energy number, you take the difference and you've got the change in internal energy. Well, initial energy and final energy are the positional energies. Now, graphically, this is represented on some type of energy, relative energy scale, and going vertical, increasing, decreasing, but all of its energy. And that now for a chemical reaction going from reactants going to products, we have two options here. Excuse me, I'm sorry. Endothermic and exothermic is where I'm going. So you can have reactions that are endothermic and reactions that are exothermic. The system is losing energy or the system is gaining energy. Let's say we just choose this line right here and this position as the positional energy of the reactants. EP reactants. Right there. The reaction takes place, and at the end of the reaction, we find the products up here. Positional energy of the products. And this would be, of course, the E final, and this would be the E initial. In this case, where final is larger than the initial in this scale. I think you recognize that. So we are having a net increase in internal energy. And that's endothermic process when you change to the products being at a energy level higher than where they start, and vice versa. If we have a reaction whereby the positional energy of the products, let's call this case 2, and I'll put a little subscript 1 down here, case 1, case 2, are below the reactants right here. Well, this would be a case of the product having a lower energy than the initial energy, and of course this is a net loss in internal energy. And so the loss in internal energy is exothermic, and the gain of internal energy is endothermic. Now you've seen these kind of graphs before, but they were called transition state diagrams, in which we had a little curve go way up here and then come back down to the position of the products, or went way up and then went way below the initial points to generate the product as we know it. Now, to understand the chemical end of this, now this is mostly, I spent most of my effort on definitions, trying to develop a language with you. Now we need to talk about, well, actually what's happening in the chemistry of what's going on. Well, if we take H2 gas plus half mole of O2 gas goes to H2O, water and whatever. Hydrogen has a structural formula that looks like that, and oxygen has a structural formula that's a double bond like that, and the water has a structure looks like this according to the molecular geometry rules. It's called a bent angular geometry. Just from the visual imaging there and there, the structure's different. So the reactants have structural differences than the products. This means that the reactants have a different internal energy than the products. Now, whether that's endo or exo, it's just the point. You have structural internal energies. The other part of that definition of internal energy is state of existence. Now, that's easier shown. This goes to, say, liquid form. But water, let me write that down, state of existence. Well, the reactants start as gases. I think that's obvious. And we wind up liquid. That's obvious. In order to stay in a liquid form, energies are different than in gases. Gases have a high energy and they bounce around. The easiest way to look at that, and just as a back of the mind reference, state of existence, solid, liquids, gases. Ice, water, steam. Okay, now we still have water, H2O, in each of those cases. But if you picked up a lump of ice, and how does it feel? You'd say cold. If you put your hand in some room temperature water, okay, you'd just say, well, it feels like room temperature, turbid. You stuck your hand in some steam, you probably wouldn't leave it very long, but you would say, oh, that's steam, vapor, like that. Intuitively, we know the difference in energy content. The ice has a lower energy, energy-wise, than the water, and the water has a lower energy than the steam or the gas phase. So when we talk about changing energies, we're not talking just about structural energies. You also have to take into account the state of existence. That is hot, cold, solid, liquid, gases. All that rumbles into together. Okay. I think we've pretty well set the stage now for analysis and the analytical aspects of the. Okay, this section is analysis of systems, reactions in our case, physical or chemical, using the first law of thermodynamics. All our calculations in this will revolve around the changes in internal energy. However, remember that internal energy is only one of the three types of energy. I better make that, according to the law of conservation of energy, energy is neither created nor destroyed. This you're very familiar with. It is only changed in form. The classic equation for total energy of a system is equal to the sum of all the classes or forms of energy. Change in energy kinetic plus change in energy positional potential and change of internal energy. Like that. The analysis that we're about to go through focuses primarily on changes of internal energy. And so as we go through this, that is the focal point, is the change in structural and state of existence. The first law of thermodynamics applied to chemical and physical processes is given by an equation. And that equation, of course, I'll put the I in there, internal energy, is the internal positional energy, EP initial, minus energy positional, internal positional energy, initial. Final minus initial on the energy scale, vertical, that we showed you earlier. If you have the big final energy number and the initial energy number, take the difference and you got it. Okay? Now, it's not as direct as that. From this, it grows the first law equation as heat of reaction plus work reaction system issue. I'm just going to leave it. Work of the reaction on the surroundings or the surroundings on the system. With just two terms. So delta E initial total internal energy change now is heat of reaction. Now that's usually a Q. I told you there was capital Q's, lowercase q's, delta H's, delta E's, and all that. This is an energy. This is a heat of reaction right here. This is a number stuck on the end of the equation. Comma, delta H reaction equals minus 900 whatever kilojoules plus W. So there's your simplest form. My job is to teach you how to use it and apply it in through the first law of thermodynamics, chemical systems. When you look at this, there are two independent calculations that have to be done in this equation. One, delta H, or the heat of reaction, and two, the work that goes in the reaction. Two of them. This leads to two possibilities out of this equation. Science has defined these two depending on how work, and heat are determined as open systems and closed systems. Open system thermodynamics occurs if work does not equal zero. That's the simplest definition I can give you. Work does not equal zero. Meaning that both heat of reaction and the work of that reaction has to be taken into account, and calculate numbers, plug them into Q, W, add them together algebraically, and you get a number that's the change in internal energy. Or a closed system, here work does equal zero. That is the defining issue. And the term work, is it zero or is it not zero? In chemistry, the equation delta EI equals Q plus W is translated into what we call heat of reaction and work of reaction. Heat of reaction is called enthalpy and is given a delta H of reaction. The circle means standard thermodynamic conditions. That's 25 degrees C and 1 atmosphere. So it's just all the tables in the back of your chemistry book, you look at the top, it'll say 25 degrees. So everything's at 25 degrees. And enthalpy is substituted for the Q in here. And I'll keep the delta EI going as we go. Plus work. Okay. So we now have a delta H of our reaction, standard conditions, plus the work. Now, to understand this part, the work part of this first law equation, we have to go back to the definition. Is force times a distance. I'm at the lowercase d. And we want to find something that will substitute for this force issue that applies to chemical reactions, and that is pressure. Because chemical reactions, the gas phase exert pressure, and we would measure that, and I'll relate it to the reaction. That is, pressure, P, is equal to force per unit area. Okay? So I can solve this force per unit area equals pressure for force to equal, multiply both sides by area, and I'll have pressure times area. Well, if I'm going to get the area of a sheet of paper, how would I do it? I'd measure the width and the length, and I'd have length times width. So I'd have pressure times length times, say, width, a distance. Length, a distance, W. And so I'm going to substitute this
force term here into work. So now we come down to work is equal to pressure times, I'll put this in parentheses, length times width times depth. I call it depth because D is a distance, another distance, depth. Well, length, width, and height is volume. So this term now becomes pressure times delta V. That's a good old ideal gas law if you're ever playing with it. PV equals nRT. So now we can substitute that term for work now. And so our internal energy, this is the first form. Well, actually the first form is final minus initial, okay? But this is the first form that pops out of that. This is the second form, enthalpy plus work. And then we rework the work term. And so now our form of changing in internal energy is delta H of the reaction plus P delta V. It is from this equation we can define open and closed systems. An open system work open system work does not equal 0. Closed system work does equal 0. If work equals 0, that would mean volume would have to go to 0. 0 times pressure just leaves us with this in a closed system right here. So delta V equals 0 is the ultimate reason the first law equation becomes a closed system. If delta V is 0, it's a closed system. That's the definition. Now I'm going to show you the differences here in the two. This reaction can be written one of two ways. One in which the delta H is detached from it, and we put it out here as delta H of reaction to equal minus 91.8 kilojoules. So that's your notation. The negative in here indicates exothermic. An exothermic reaction. Or I can write this and include the number in the equation by placing it on the right side of the equation. So by putting it on the right side, I have to use a plus. We don't use any negative signs in. You don't go 2NH3 gas minus. It's the fact that it's listed on the right side specifies exothermic reaction. If I want to evaporate water, this is simple. Liquid to H2O gas. I have to put into that 540 calories to change it from liquid to gas. So delta H reaction is equal to 540 calories, CALs. I did not put a sign out here. It is understood to be a plus, okay? Or you can write this H2O liquid plus and put this on the reactant side as though it were going into the endothermic reaction. 540 calories goes to H2O as a gas, and so that's endo notations. So I'm sure, don't mean to insult you or anything to repeat that, but I just want to be sure everybody's on the same page. The number on the right side of the equation, included in the equation, is exothermic. The number on the left side of the equation, left of the arrow, is endothermic. If the number is listed negative, detached from the equation, it's exothermic. If it doesn't have a sign there, it's assumed to be positive and endothermic. Now, I'm going to repeat what makes a system open or closed is the work. And more specifically, in the work, the change in volume. So when we talk about the change in internal energy is Q plus W, and W does not equal 0. In other words, we can have delta EI equals delta H of reaction, common at standard conditions, plus P delta V, and delta V, which is responsible for making work 0 if it was going to be 0, or not 0. Delta V is not 0. In chemical reactions, we compare the molar volumes of the products to the molar volumes of the reactants. If they don't equal 0, when you take the difference, it's an open system. Okay? The one I just used, ammonia synthesis, is an excellent because all the coefficients are different. 3H2 as a gas plus N2 as a gas goes to 2NH3 as a gas. Question is this an open or closed system? It is an open system. Why? Delta V does not equal 0. When you look at this, the reactant side has 3 moles of hydrogen gas, 1 mole of nitrogen gas. Collectively, that's 4 molar volumes. VM, 4 molar volumes. At STP, 0 in 1 atmosphere, that BM is 22.4. If not at standard, it's something else. On the product side, you have 2 moles of gas, which means 2 molar volumes of ammonia. So the change in volume, molar volumes, is 2 VM minus 4 VM, and that equals a minus 2 VM. That ain't 0. If we take a reaction like this and take the difference in the molar volumes, and it comes out negative. New term coming up. We call this a compression reaction. Because you're starting with a large volume over here, 4, listen to me, and going to a smaller volume. Large volume to a smaller volume. Compression. Reaction. Still an open system, but it is a compression reaction. Another example, the water going to H2O gas right there is also an open system. Listen to me if you hadn't listened to me so far. There is 1 mole on the left and 1 mole on the right, but the one on the left is liquid. It ain't gas. So Vm over here is 0. Liquids and solids are 0 molar volume. When you go over here to the product side, you see gas, that is 1 molar volume. This is from a 0 to whatever a molar volume is, and that's called an expansion reaction. Like the balloon's blowing itself up all by itself. So, regardless of whether it's showing a decrease in volume or an increase in volume, if that difference in volume between the reactants and product side is not 0, then those are open systems. If they are open systems, you have to apply 2 calculations. The first calculation is your heat of reaction. If you remember Hess's law from Chem 1 or any of that, we added up the standard heats, and we'll do it here again in this. Standard heats of formation of the reactants, standard heats of formation of the products. Take the products minus reactants, you get a delta H number. Have you ever done that before? I don't know. That's heat of reaction. Okay, that ends delta H calculation. The P delta V calculation requires that you come up with a pressure and volume, unless you got a professor that knows how to make that conversion and make it real easy for you. And that I hope I can do. Now, determine the change in internal energy of the following reaction. And this is the ammonia synthesis that we just saw, and we identified as an open system anyway. And at the end of this, you will have the delta H number attached sometimes. If you don't, we'll get to that in a minute. Hess's law has to be applied. The total internal energy is the Q plus W, which is equal to delta H plus P delta V. But after painstakingly going through the calculation of work using P delta V, I found a common equation to put there that makes this whole issue very easy. But you have to understand the calculation is absolute, and then you have to make an interpretation, which I'll show you right now. Delta H plus 2.5 delta V, absolute value. Then you make an interpretive assignment of sign, S-I-G-N, which would look something of the part and you'll understand after I go through that. What sign do you put there? Plus or minus? If it is a compression reaction, that is, we're going from 4 to 2, like we showed you. It's like taking, listen, watch me. Please concentrate and listen to what I'm saying. It's like taking a balloon and squeezing it down to smaller volume. What do the molecules do? They push back on your hands. Why? Because they gained energy. Think of that. Squeeze the balloon, molecules gain energy, and they push back on your hands. That's endothermic when you have a compression. You put a plus right there. Can't push them together because they're pushing back on you. More energy. If it is an expansion reaction, assign a negative
that is like in the evaporation. It's like removing the walls of the balloon and letting the molecules float out into space. They will relax. That's the way I see it. That's the best analogy I can give you. And when they relax, they're losing energy. So we assign a negative to the issue in that position. So this is your equation. So let's see how we apply that here. So we want to get delta E internal is delta H of reaction plus 2.5 delta V, and I just always drop and just remember I'm going to have to put a sign in that thing anyway. Well, the delta H is already here in this case. And remember what I said, they're separate calculations. You do the heat of reaction. When you're through with that, then you go to work, you can make that, put them together then. So the heat of reaction is a minus 91.8 kilojoules. Right there. Finish. Plus, then I'm going to do my work function. 2.5 times the change in volume. Well, we went, the change in volume is from 4 molar volumes to 2 molar volumes, so that's a 2 Vm decrease. What do I put here? I just put a 2. That's all you need to do. Whatever that delta V is from the equation, you put a 2 on there. If it is a compression reaction, then I need to put a plus right there. And so there is, and this will come out in kilojoules. And so this is a minus 91.8 plus 5.0 kilojoules. Comes out 86.8 kilojoules net change in internal energy. It's a very simple calculation if you've got all the symbology in the chemical equation. In this case, just pick them out and plug them in the first law equation. That's all you got to do. The work function here, 5 kilojoules, is very small compared to the delta H of reaction. In many cases and publications, you won't, the scientist, publisher, author will not even take that into account. It is my obligation to teach you the difference between open and closed systems. Maybe there is an application out there that you have to take that into account. I can't think of one. Most of what you will see published in the textbooks will have this equation, comma, delta H is this, that, and other, and didn't take anything into work. Because it's so large, the overall outcome of this is still exothermic to the tune of 90 kilojoules in terms of size of number and so forth. This is getting real picky about the outcome, but you're still responsible for it and the work we're doing. But that's an open system. One more. Calculate delta EI for evaporation of water. Delta H of the reaction is equal to 80 calories per gram, which is equal to, depends on how you want to do it. Let me give you this. 1 calorie equals 4.184 joules. So we can multiply that 4.184 joules per calorie. This is a sidebar here in case you want to do it in joules.
So 335 joules per gram is the standard heat of vaporization for water. So in this one, H2O as a liquid goes to H2O as a gas. Now, I didn't give you an energy number here. What we'll have to do is use Hess's law. Hess's law requires that we take the difference in heats of formation of these substances. Standard heats of formation are found in the table right here for different substances. For water, as a liquid, there's a minus 285.8 kilojoules. Kilojoules per mole. Well, we only have 1 mole there, right there. And as a gas, it will be 241.8 kilojoules times 1 mole. That's just per mole, but each equation has 1 mole in there. So the delta H of the reaction by Hess's law says that I add up the delta HS for the products, that's what this says, and subtract from that the delta H of the reactants. Well, we only have 1 item in each side, so that makes it real easy. So delta H of reactants products minus 241.8 kilojoules minus a minus 285.8 kilojoules. And so that comes out 44 kilojoules plus. So I take that up here, semicolon, delta H of the reactant standard conditions, because I use standard heats of formation, 44 kilojoules. We'll work some more complicated ones later on. I'm just trying to get through the concept. Hopefully you know about Hess's law. If you don't, we will repeat this. Okay, so we need the total internal energy of evaporation. Well, I have to have the change in volume. Well, what's the molar volume over here of this liquid? How big is that? Is it a 0? Yes. Okay, so I have 0 Vm right here. Over here is a gas, and there's no coefficients. That means 1 molar volume over here. So second minus the first means that we have an expansion of 1 molar volume. Okay? Everybody good? Any questions? Okay. So now we're ready to calculate the total EI. Okay, so our delta H, I'll put it up here. Put the plus in for emphasis. Plus 2.5 times 1. And since it's an expansion, what sign do I put in here? Negative, because it's an expansion. Molecules are relaxing. So I'll get a little negative and just squeeze it in there, right there. So now it's 44 minus 2.5. Everything's going to come out in kilojoules. And so the net change in internal energy is 41.5 kilojoules. The work function is still so small, it really doesn't make a lot of difference. So most people just say, well, they'll just work off 44 kilojoules in the heat of reaction for other applications and stuff. So you can see there's not much, but you will be responsible for making that simple calculation. Okay? The topic requires two calculations, one independent of the other. Then you combine them. Delta H of reaction, heat of reaction, and work of reaction. Now, point of issue. All of the work that you will have to be concerned about is 2.5 delta V. I think everybody can handle that without any trouble. But that's taking into account we're at 25 degrees and 1 atmosphere. When you go to next school, engineering courses, you may have to go back to the P delta V. And to keep things simple right now, that's as far as we're going to go. So keep in the back of your mind, you may have to start using kilopascals and converting to energy numbers in the future. Keep in mind, if it's a compression, work is greater than 0 plus an endothermic. That's just the work function right here. Or expansion work is less than 0 or negative and is exothermic work. That's not the overall delta E, that's just the W. The way you have to take that into account. Now, expansion compression is how your textbook or the Ebbing textbook presents it. But what I'm going to do right now is going to write down the first law equation. Both will be correct. Both of those are correct. The reason they're correct is that when you calculate your change in volume over here, you take the change in sign along with the change in volume. Over here you had to assign a sign when you considered change in volume to interpret it as compression or expansion. Here. Going back to the ammonia real quick, show you how it works. Okay. Using delta EI equals Q plus W, we use delta H plus 2.5 delta V. And we came up minus 91.8 kilojoules plus, all right, that is a compression, so that would have to be a plus 2.5 times 2, and all that's in kilojoules. And so we came out with 86 point something or another, I don't remember. So here it is in the Q plus W. Or, here, we go delta E equals Q minus W, which equals delta H of reaction minus 2.5 delta V. So run your delta V out of this. There's a decrease in 2Vm from reactants to products. I think everybody sees that. And so insert a minus there. A minus delta V there. And what do you get? Minus 91.8 for that term, minus 2.5, and it decreased by 2 molar volumes. So what's the outcome? It is minus 91.8, less than kilojoules, don't forget my units, 91.8 plus 5.0 kilojoules, and guess what? Same number. Well, why present both of them? Because in your textbook, I'm obligated to teach the adopted text material. However, you go to engineering courses, you'll find that the first law will be listed as Q minus W. Both of them are the same, except the engineering text take the sign into the delta V analysis. And you won't have to go through this expansion compression interpretation. So that, I don't want you to get to the next level and say, Doc's lied to me or something. Okay. In closed systems, delta H of reaction plus P delta V. I'll just use that. For a closed system, delta V equals 0. Therefore, delta EI equals delta H of reaction plus P delta V, and this goes to 0 because delta V is 0, and ultimately the heat of reaction at standard conditions that you calculate from Hess's law like we did earlier is just the heat of reaction here. So internal energy and heat of reaction only are equals Q. That's a closed system. Summarizing it real quickly, that's the closed system relationships. Now listen, and we'll start here next time. There are 3 scenarios that are closed systems in the issue of this. A, when the sum of change in molar volumes of the reactants equal the sum change in molar volumes of the products. I2 gas plus H2 gas goes to 2HI gas. 2Vm, closed system. Number 2, or B, is called a bomb calorimeter. Bomb calorimeter. This is a steel-jacketed piece of equipment. Water all around this steel-jacketed reaction chamber. You put a substance down here on a stage, run electricity through it, and ignites. It's all combustion reactions. Heat goes into the water. You measure the temperature change over here. No volume change. This doesn't expand or compress at all. So the only thing that comes out of a bomb calorimeter is the Q value, or the heat reaction, just about through. Delta V equals 0, which gives closed system. And we have what they call a calorimeter equation. Standard is a capital Q, constant volume, is equal to the mass of substance you're reacting times, calorimeter constant, C sub V, the specific heat, heat capacity of the calorimeter constant times the delta T. So all you measure is the delta T, and you're given this. See, this comes from the manufacturer. So say 200 kilojoules per degree Celsius, and you said 10 degrees is whatever your standard is times temperature. And the last one, and I'll let you go, is what we call solution phase reactions. Delta V is considered to be so small that it's zero. It's like you have a solution of acid, 100 milliliters of strong acid, plus 100 milliliters of strong base. You pour them together, you get a reaction, but when you finish, you have 200 milliliters total. That is not an increase or decrease in the net effect of the reactions system. And that gives delta V equal 0 and closed system. Next class we'll work problems in each of these. Second law, and so forth. Thank you for your patience. Now look guys, give it your effort. Remember, we'll start with a quiz on this stuff. Have a good day.
Afternoon, Doc.
Review my video. Memorize them. You got my address. All right. Hi.
Is everybody done?
Hi, y'all.
Can you pull it
I
that way?
pull and push and yank and tug.
Okay, just right there. It's good.
Okay. I can take it up here now. Instead of taking a picture of your finger. Look, see, that's what you're taking a picture of.
My finger.